Hello and welcome to yet another video of Cornerstones of Math. Today we are going to solve these two problems that are quite similar. In both problems, we need to find the function fx that satisfies certain integral relations. So the problem itself is pretty straightforward. But what do these relations imply about our unknown functions fx? Let's first start with this ln. One important property of logarithmic function is that it grows slower than every algebraic function. That is, whatever algebraic function with whatever power you have, it eventually catches up the logarithmic function. As for the exponential function though, it is the function with the property of increasing faster than every algebraic function. Whatever fast-growing algebraic function we have, the exponential function eventually catches up. So in the first problem, the interval of integration increases very slowly because we have logarithmic function in it. But the resulting integral is the exponential function, which is the function that increases super fast to use the common terms. So what kind of function would fx might be to give such relation? And as for the second problem, what kind of function would fx need to be so that the resulting integral is the very slowly growing logarithmic function, even though the interval of integration grows extremely fast? Well, let's find out. In both problems, I am going to introduce the notation for the antiderivative of our unknown function fx. So let capital Fx be the one of the antiderivatives of small fx. Then, by the fundamental theorem of calculus, the left-hand side can be written as capital F of ln u minus capital F of 0. So this equals e to the power of u minus e for all positive number u. Next, let us differentiate both sides with respect to u, because that will give the expression containing small f. So first, we have small f of ln u. But this is the derivative with respect to ln u, not u. Therefore, according to chain rule, we must differentiate ln u with respect to u, which gives 1 over u. And differentiating this constant capital F0 simply gives 0. On the right-hand side, we have the derivative of e to the power of u minus e, which is just e to the power of u. So we have small f of ln u equals u times e to the power of u. In order to obtain fx, we simply make a substitution ln u equals x. This gives u equals e to the power of x, so we have fx equals e to the power of x times e to the power of e to the power of x, which can be also written as e to the power of x plus e to the power of x. And from this result, we can make sense as to how we obtain a fast-growing exponential function even though the interval increases logarithmically. Our integrand function, fx, is the function that increases even faster than conventional e to the power of x. Now the second problem, and we do similarly. We introduce the antiderivative capital Fx, then the left-hand side equals capital F of e to the power of u minus capital F of e. So this equals ln u. Differentiating with respect to u, first we have small f of e to the power of u, but then again this is the derivative with respect to e to the power of u. So we have to differentiate this e to the power of u with respect to u according to the chain rule, which gives e to the power of u. And on the right-hand side, we have 1 over u. Therefore, we have f of e to the power of u equals 1 over u times e to the power of u. So this time, we let e to the power of u as x. Then u equals ln x. So we have fx equals 1 over this e to the power of u equals x. And u equals ln x. So we have 1 over x ln x, and it is given in the problem that fx is defined only on x greater than 1, since the given integral relation is only able to cover this region. So this is our final expression for f(x). So this time we have the integral of a decreasing function like y equals 1 over x. However, our function f(x) has additional ln x in the denominator, so it decreases faster compared to y equals 1 over x. That's why even if the interval of integration grows exponentially, we only have logarithmic function as the result of the integral. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.